Hi, I'm going to show you the last of the papers of my PhD thesis with the title Mitigation of Environmental Effects of Frequent Flow Ramping Scenarios in a Regulated River. It contributes to Objective 2 in the thesis by presenting a case study where Lidar data is unavailable. It highlights the extensive fieldwork required and the necessity of integrating multiple data sources to obtain a reliable bathymetric foundation for analysis. It also aims to investigate the effects and mitigation of hydropeaking, including the high-frequency start-stop scenario. And what we have here is that the river doesn't have bathymetry. So we have just the side channels where this was no water when the leader was surveyed. So if it was dry, okay, we can measure, but anything that was dry, we have no data. This is a picture of the actual river. So, and here there is also the effect of hydropeaking. We have this lake, Jones Pane, upstream, and the water will normally go this way. But for increasing the potential of hydropower, the water is going through an underground tunnel, 8 kilometers, 10 kilometers long, until the power plant. And in the power plant, the water is released again to the river, the natural river. So what happens is that we find in this area strong flow fluctuations. This area here is the last reach. We have the outlet here where the water comes out, and therefore these strong fluctuations occur. The water fluctuates between 35 cubic meter per second up to 130. The minimum flow in this bypass area, in this natural section, is 35 cubic meter per second. So it's actually a quite high flow for minimum flow. This is the 8 kilometer reach that we are going to study, and this is where the thesis was presented in NTNU in the city of Trondheim, in campus of NTNU. So what we did was first collecting all the available data. There was available data from NTNU, from the university, also from the commune, from the community, the town hall, that collected some data here. Also, a private company shared with us all this data, but we still have a lot of gaps where there was no data at all. So what we did was going to the river with the ADCP and yeah, we collected all this. I'm gonna just stop it by doing these kayaking measurements. And finally, well, this was measured in one day 2, day 3, day 4, and day 5. This was 5 days of fieldwork, but it was a lot more days of data processing because once the data was taken, we have to get the ADCP and also all the different matches that we have to do to get all the reference systems together was quite challenging. So it was an actual work that took months. First, because we were all also people from university doing and learning, but I will think also that if a professional person does it, it will take time because you have to get familiar with the different instruments that have been used, which reference systems were used at the moment, and matching all the data together. Also, we took the topographic Lidar that was available online, so the part that were not wetted when they were surveyed, and we got this final data set. We can also see that even though our measurements were really good, we still have some areas where there were small gaps. This is so because the ADCP also encountered challenges when the water is very fast. I can show you here an example. This is the first day we were serving. This is myself with the computer. But you can see that the ADCP does like this zigzag track. But sometimes if the water goes too fast, it is not possible. So this is where we encounter, like for example, in this ridge here, a gaps in the data. This is the model that we did. You can see the 2D flow area, computational points, break lines, downstream boundary condition. We also took a lot of validation data. So we measured 42 points containing the water surface elevation at 85 cubic meters per second. And we did this calibration. And I want you to show here the calibration that I didn't show in the previous models, because for this area here, we could see that the best fit was for a Manning number of 0.09. Okay? The best fit is for a Manning number of 0.09. And this is actually quite high Manning number. This is a very high Manning number. We usually get between 0.35 to 0.06. 0.09, we could say it's a rare number to have. And I think this is this way because in this area, the actual measurements are not as good. And when we come to calibration, we force Manning numbers, for example, to get the model to do what we want to do. And this is maybe we are forcing the water surface elevation to be as they should, but maybe the velocities are not as accurate. So I do think that even though we can calibrate, having good data is the basis. And it's always more important than getting a good calibrated model. But of course, always with calibration, we can compensate. This is a comparison we did with orthophotos for 97 cubic meter per second. This is the main bridge in the city center. And also, we did the simulations. And we could see, for example, in this area here, we have two sites that are critical for stranding. First, this one here, this is a picture that I took with a very low flow where actually we could check, we could see the model and say, okay, something is happening here. So we went to the field and it's like, yes, this happens. This channel gets dry when the water flow is low. And we also observed a small fish that was blocked in one of these pools. So it was lucky that it made it to one of the pools because maybe it could just stay in one of these dry areas and we will not survive. We also observed this channel here, where we also went to the field and tested that, okay, yeah, this is happening at low flow. This side channel over here is not connected. Then we did simulation for start-stop scenarios, so stopping the turbine very fast. And we created an hydrograph. This is the normal hydrograph with the turbine shut down. But we also created an hydrograph where in all these points, there are risk areas for the fish to be stranded. The watering rates, remember from paper one, the watering rates, the velocity in which the water drops is not higher than 13 centimeter per hour. And this way, the mitigated hydrograph is created. The objective was to study a core Ercosian underground reservoir, but this wasn't feasible. This was just a research study, but I will not go deeper into this today. But what we show, what we see in this mitigation paper is that, okay, we can do great results, but the time that it took to get the data was still very long. And yeah, I think it's a big difference to having a good Lidar data set. And we also forced the calibration. So just to wrap up the thesis, I want to conclude with two things. Like from paper one and paper two, we show that high precision Lidar data significantly enhance the accuracy of 2D hydraulic modeling, enabling detailed assessment of stranding areas, rapid hydropeaking effects, and flood mitigation strategies. And these studies demonstrate that integrating LiDAR data supports the development of more environmental sensitive and technically sound river management practices. So paper 1 and 2 shows how good LiDAR is for assessing these hydropeaking events and also helps a lot when it comes to flood mitigation strategies. While paper 1 and 3 or 4 shows that in the absence of LiDAR, environmental and hydraulic assessments suffer from reduced accuracy, requires extensive fieldwork and multi-source data integration to compensate for missing high-resolution terrain data. These studies emphasize the trade-offs of limitations of traditional flood modeling approach while identifying optimal leader point densities to improve simulation fidelity and impact assessment. I hope you like it. Do you have any questions? You just can put down there. And thank you for listening. Have a great day. Bye-bye.